it up. Okay, I'm going to finish up the free response 2010 question number 4. This is part 2 of the video. This is an area problem, and they do throw some different things at you on this one. R is the region that is bound, and they give you the graph, and they give you the function, and they give you the horizontal line y equal to 6. Find the area of region R. Now, in this problem, when you're finding the area, it's a classic top minus bottom problem, and they tell you that you're starting at 0 and you're going to stop clearly at 9, and the area, the top line is 6 and the bottom is the curve, and you find the antiderivative by hand, which is quite reasonable in this problem. You evaluate carefully and you get an answer of 18, so that's hopefully 3 easy points. Part B, they ask us to write a definite integral but not to evaluate it that gives the volume of the solid when we rotate about the horizontal line y equal to 7. Now the line y equal to 7 is up here. It's horizontal, so we're revolving it around, so we are in terms of x. So that's going to be important. And there's going to be a hole in the graph. So we're going to have a pi, we're going to have a big R square, which is the distance from the axis of revolution to the outer curve, top minus bottom. So big R is going to be 7 minus the square root of 2x, and little r is going to be the distance from the axis of revolution to the inside curve, or top minus bottom, so 7 minus 6 is going to be 1. Make sure that you square those independently of each other. Now they wrote 7 minus 6, but we know that 7 minus 6 is 1. And so hopefully you have your pi out front, and you have your correct bounds, and you have big R squared minus little r squared. Part C, region R is the solid of a base for each y. Now they're already telling you that you're going to be working in terms of y, you're going to be working in terms of y. They're cross sections, so we're making a cake. They're telling us that the slices, this is the key right here, the slices are perpendicular to the y-axis, so in terms of y, in terms of y, in terms of y. We have a rectangle whose height is 3 times the length of its base. So remember, when you're making the cake, you always start with area. The area of this particular rectangle is height is 3 times the base, so it'll be base times height, but the base is 3 times, the height is 3 times the base, so 3b times b will be 4b squared. So that's the formula that we're going to be dealing with here. Alright, now we have to figure out the length of a slice. So let's go back up to the diagram, and let me get rid of what's already here. Okay, a slice, since it's perpendicular to the y-axis, will be going in this direction. So that's going to be the distance from the y-axis to the curve. Now the curve was given as y equal to the square root of, or 2 square root of x. So we need to solve for x, and we get y over 2 is equal square root of x. We square both sides, and we get y squared over 4 is equal to x. So that's going to be the length of the base. So that's my b right there. Okay, so I'm going to come back down and go back into my formula. So my formula was 4 times b squared. What was b again? Y squared over 4. So y squared over 4 quantity squared, which is 4 y to the 4th over 16, and 4 divides into 16 4 times, so I get y to the 4th over 4. Okay, now I'm wondering why. Oh, that's the same. No, where did they get through? Oh, because I'm an idiot. Oh, uh-oh, that's on a video now. 3 times 1 is 3. I hope that you are better at multiplying than I am. So this is a 3. This is a 3. It does not divide out. I apologize. So I get 3y squared over to the 4th over 16, which is what they have right here. And we're going to collect the area in terms of y from 0 to 6 of 3/16 y to the 4th dy. And I think they only asked me to, again, set it up and do not evaluate it. Wow, I can't believe that I multiplied this and got 4b squared. Alright, so hopefully you understand what my mistake was, and you probably caught it before I caught it myself, but yay for me. Alright, next problem. Problem number 5. We've done this problem and done this problem and done this problem and done this problem. It's pretty basic until you get to the last part. Find g of 3 and g of negative 2. Well, here's the scoring guide. We know that g of negative 3, you take the initial condition, you collect the area, and you do the same thing for g of negative 2. You're going to collect all that area using geometry. Now, just when you're going from 0 to 3, here's 0, and we're going all the way to 2, we're going all the way to here. Now this part is simply a triangle, so we're going to do 1/2 base times height. That's easy. But this region right here, it is a quarter of a circle, so it's pi r squared over 4, and the radius is, what is the radius of this thing? The radius is 2, so, am I right about that? Yeah, the radius is 2, so 2 squared is 4 over 4, so that area, that quarter circle here has an area of pi, and then you're going to add that to the triangle area. And again, don't forget your initial condition, and then you're going to do, when you find g of negative 2, remember you are moving backwards from 0 to negative 2. So when you go from 0 to negative 2, I'm going to sneeze here in just a second. So 0 to negative 2, this region also excuse me, has an area of pi, but because we're going backwards, we're going to negate that and make it negative pi. Part B, find each x coordinate for the point of inflection for the graph of y equal to g of x. So we are looking for, let's say, g of x, this is the graph of g prime. So if we're looking for points of inflection for the original function, we're looking for where the first derivative has local max and local mins. So take a look at the answer. The graph of g has points of inflection at x equals 0, x equal to 2, x equal to 3, because the first derivative changes from increasing to decreasing at x equal to 0 and 3, and from decreasing to increasing at x equal to 2. Okay, so there would be the local mins and the local maxes of the graph. What was that? 0, 2, and 3. I'm just looking. Yep. And then part C is a little bit tricky, and I will admit to that. In part C, they give you a new function, and the function is called h of x, but it's defined using g of x. They want the x coordinate of critical numbers of h, and then they want to know if we have a local maximum or a local minimum. So I know that you are aware that you take the first derivative of h and set it equal to 0. Well, the first derivative of h is g prime of x minus, and we're going to use the power rule, x squared. So that's h prime of x, and we have to set that equal to 0. That's not x squared, that's x when you find the derivative, sorry. Alright, so in other words, that means that whenever g of x is equal to x, then the first derivative is equal to 0. So this is a little bit tricky, so look at their answers. Now what that means is, since it says x is equal to g of x, I'm looking for points whose x coordinate and y coordinates are equal to each other. Like on the line y equal to x is basically what that's saying. The x and the y's have the same coordinates. So I'm going to take, I can look at the graph back up here and see, well, here's clearly the point 3, 3. So that's a place where the x and y have exactly the same value. So that means at x equal to 3, the derivative is equal to 0. So that's one of my critical numbers, and you can see that they have identified that right here. Now the question is, see, on some parts of the graph you can't really identify that. On the line segments you can. So the next thing they're doing, now this is the crazy part, I don't know if you would think about doing this or not, you've actually got to find the equation of that semicircle and actually set it equal to x. Again, the other parts right here, this was linear, and this was linear, and I can see 3, 3 very clearly, and I can look on these linear parts to see if the x and the y values, x and y have the same values on the lines. But now I actually have to find the equation of that semicircle. Now remember, the equation of a circle centered at the origin is x squared plus y squared is equal to r squared. And so r is 2, so we get x squared plus y squared is equal to 4. I'm going to solve that for y, and I get y equal to, I want the positive side because it's on top, so I'm not going to do plus or minus, 4 minus x squared. So that's the equation of the semicircle, and I'm going to set that equal to x, and I'm going to solve that. Let's see if I have some room down here to show you that. So I'm setting square root of 4 minus x squared equal to x. I'm going to square both sides. That takes off the radical. 4 minus x squared is equal to x squared. I'm going to add x squared to both sides, and I get 4 equal to 2x squared. I'm going to divide both sides by 2, and x squared is equal to, now you may be thinking, well, let's get the 2, and x is equal to, you may be thinking, plus or minus 2. However, if you look back at if you think about negative 2, if x is negative 2, and we're looking for when the x's and y's equal to each other, if x is negative square root of 2 on the graph, come on graph, where are you? Negative square root of 2 would be like over here somewhere, and he has a positive y value. Over here, positive square root of 2 gives me the same y value. So that is also a candidate as a critical number. Now I admit that this is a pretty challenging problem. So this is another critical number, and then you have to decide whether the graph, whether h prime is changing from positive to negative or negative to positive. So I don't know. Hopefully, if you were able to at least find the derivative of h, you got a point. If you identified both candidates, you got a point. So I'm guessing if you didn't get square root of 2, you probably didn't get that. And the analysis, it's kind of hard. So if you got 5 points, 6 points, that's pretty good for this problem, because I would say this is a pretty challenged problem. All right, but don't be discouraged on the AP test if you think, like you get to number 5 and you think that's challenging. That doesn't mean number 6 is going to be impossible. In fact, this is a pretty reasonable number 6. They give you a first derivative and they give you a second derivative. They tell you that you have a particular solution to the differential equation, and they give you initial condition of 1, 2. In other words, that's one of the particular, or that is the particular solution to this equation. Write an equation for the line tangent to the curve at x equal to 1. Well, that's pretty reasonable. They give us the x value and the y value, so y minus 2 is equal to the slope. That's not bad either. I'm going to take x and y. I'm going to go over here and get the slope. And 1 times 2 cubed is 8, so I'll have 8 times x minus 1. And so there we go. We get 2 points for that. That's pretty nice. Part B, we're going to use the tangent line that we just found to approximate 1.1. Well, that's pretty easy too. I'm going to plug in 1.1 here, subtract, multiply by 8, add 2, and get an output. That's not bad at all. And I get 1 point for getting that approximation. The next thing they asked me to do, now this is linearization. We need to figure out if the tangent line is above or below the curve. If the tangent line is below the curve, the approximation is too small. If the tangent line is above the curve, the approximation is too large. So in other words, if the curve is concave up, the approximation is too small. If the curve is concave down, the approximation will be too large. So we need to know about the second derivative. Well, good news. We know the second derivative. All we need to figure out about the second derivative is whether the output is positive or whether the output is negative. So we take 1, 2, plug it in here for every x and y. We see that the output is positive. Therefore, the function, and you would need to say all this, the function is concave down, therefore the tangent line would be above and the approximation would be too large. I don't think they actually ever stated that the approximation is too large, but that's the answer. Part C, we're going to separate and integrate, and they give us a different, or is it, they give us the back to the particular solution, 1, 2. Please, 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 please tell me that you did not get ln for this. It's only 1 over y to the first power, and this is y to the third power. So the way we would integrate that, they didn't show the work, but you would have the integral of y to the negative 3 dy, and on the right hand side, that's the easy part, x dx. We increase the power by 1 and divide by that power. On the other side, we get x squared over 2 plus c. I would rewrite this to be negative 1 over 2y squared is equal to x squared over 2 plus c. Substitute in x and y, solve for c, and then notice that, yeah, they solved for y. Now this part right here, they gave the domain again, but in the scoring guide, you're going to see someone who got 9 points. They did not give the domain, and they got all the point. And you see in the scoring guide, it doesn't ever say that you have to give the domain. So let's take a look very quickly at, if the page will turn, a student who got 9 points. Now this student is a little different than some that we've seen. The work is a little more, just a little bit less and a little bit less writing. So you can see that in the first part, they substituted x, y into the derivative and got the slope. This person decided to go with y equal mx plus b format, which is perfectly fine. Point slope is also perfectly fine. You can see in part B that they did the linear approximation, and let's take a look at their answer. They say that f of x is greater than 0. Okay, that's not important to me. The second derivative is also positive from on this interval, so the concavity is up. Therefore, the approximation is an underestimate. What did I say when I was back here? You guys, I need you here to be correcting my mistakes. What did I say? The second derivative was positive, so we're concave up, so the approximation is too small. All right, hopefully that's what I said when I was going over that. It's been a long day. And then finally, for the last part, the main thing I wanted you to see here, this is in the way. The main thing I wanted you to see is when this student, notice they did not rationalize the denominator. You don't have to simplify or clean that up. But when they solved this, they did not put the domain and they got full credit. So I hope that you're finding this helpful. I hope that you find the other practice problems helpful. And when you get back, we will finish this up and do the test. Enjoy your break.